Hey guys, it's Miss Rainey. Today we're going to talk about a couple of the gas laws we haven't gotten to yet, including Avogadro's Principle, Dalton's Law of Partial Pressures, and Graham's Law of Effusion. Are you ready to get started? Because I am. Let's go! Okay, we're going to start with Avogadro's Principle. Now, I don't think I've actually said that name so far this year, but Avogadro, I think Lorenzo Carlo Amadeo Avogadro, is the person who came up with the concept of the mole. Now, he didn't actually discover that number that we've been using in class, 6.02 times 10 to the 23rd, but when that number was discovered, it was attributed to him because of what he was looking or what he was researching about the mole or about these particles of gas. So that number actually has nothing to do with Avogadro's principle. Avogadro's principle is what he was actually researching and studying during his lifetime. And that is that the volume of a gas is directly proportional, which means one goes up, the other goes up, to the number of moles of gas. Volume goes up, then number of moles goes up. Now, just like we say volume is the letter V, moles is the letter N. So N is equal to 12 moles, or N is equal to 3 moles. So volume goes up, moles goes up, as long as temperature and pressure are constant. So we're not dealing with temperature and pressure at all. So essentially what Avogadro's principle says is if you blow up a balloon, it gets bigger. Now, that seems kind of silly to just say if you blow up a balloon, it gets bigger. Well, of course, if you blow up a balloon, it gets bigger. But the reason why it gets bigger comes back to Avogadro's principle. If we increase the number of moles of gas, in other words, if we blow gas into a balloon, then the volume of that gas or the volume of the balloon will increase. So all we're saying is putting gas into a container causes the container to expand and have a larger volume. So let's see how that works with regards to the math. So if we have, say, 2 moles of nitrogen, which has a volume of 45 liters, 2 moles has a volume of 45 liters. Find the volume of 6 moles of the same gas at the same temperature and the same pressure. So now essentially all I've done is say that N has increased. The number of moles of gas is increasing. So V should also increase. The volume of the gas should increase, and it should increase proportionally. Now remember the Charles law, which was V1 over T1 equals V2 over T2. That is, volume and temperature are directly proportional. And remember Gay-Lussac's law, P1 over T1 equals P2 over T2. That is, pressure and temperature are directly proportional. So if pressure goes up, temperature goes up, or if pressure goes up, volume goes up, which means that there should be some sort of rule about Avogadro's principle, which is V1 over N1 equals V2 over N2. The volume is proportional to the number of moles. So then I can say V1 is 45 liters, and N1 is 2 moles. And so volume 2 would be the X, N2 would be the 6 moles, and I'm going to cross multiply and divide by what's left. So 45 times 6 divided by 2, let me type that in my calculator really fast. And I end up with X is equal to 135 liters. Well, that's not very pretty. Let me try that again. 135 liters. There we go. There we go. 135 liters. And we said that volume was going to go up, and volume went from 45 to 135, so that checks out. That's probably a pretty good statement. Okay, so now we're going to move on to Dalton's Law of Partial Pressures. That is, that the total pressure of all of the gases in a container is equal to the sum of the individual pressures of gases in the container. So if we said the pressure of air would be equal to the pressure of oxygen in the air, plus the pressure of nitrogen in the air, plus the pressure of, let's say, water vapor in the air, plus the pressure of carbon dioxide in the air, plus the pressure of, I don't know, pollution in the air, or whatever we have. And so all of those added together would be the total pressure. So partial pressure is just the pressure exerted by an individual gas. So that's the oxygen in air, or the nitrogen, or the hydrogen, or the water vapor. So it also says that pressure of a gas is directly proportional to the moles of a gas under the same conditions of temperature and pressure. Oop, that's a typo. That should say under the same conditions of temperature and volume. So if temperature and volume are the same, then the pressure and the moles are directly proportional. So essentially, what that's saying, if your volume cannot expand, so let's say pump up a tire. Now, when you pump up a tire, the tire does get a little bit bigger. Not significantly, but it does get a little bit bigger. But we're thinking about a tire that kind of is pretty much already full, so its volume is pretty much already set. Then we can just say that the pressure increases. Assuming that the volume is not going to get significantly bigger, so we already have a tire that's pretty much already pumped up. So we're putting more moles of gas in it. Pump up a tire is increase the number of moles of gas, and then we're going to increase the pressure. That's what Dalton's Law says. So we've got two parts of Dalton's Law, that the total pressure is equal to the sum of the individual gases, and that pressure is directly proportional to moles, assuming that temperature and volume are constant. So let's work a problem with Dalton's Law. So we got butane that it's collected by water displacement, so the gas bubbles up through the water. And I'm going to pause this right there and talk about what that means. So let's just say I have a test tube, and I fill that test tube with water. So that's a test tube completely full with water. And then I'm going to take that test tube and a bucket of water, and I'm going to put that test tube upside down in my bucket of water. So I end up with something like this: test tube full of water, bucket full of water. And so now the test tube is no longer sitting over here because it's in the water. So then let's say I have in a separate place some sort of reaction happening in some sort of separate beaker with a lid on it and a straw or a tube or something coming out of that. And that straw or tube or thing is coming up into, going through my water and then kind of stopping there. So I have a reaction happening in here, and this reaction is going to be red. And so this reaction is, once it starts happening, it's going to go through this tube, because where else is it going to go? It's certainly not in that hole, because that hole doesn't exist. So here it goes, and the red is going to start bubbling up through the water. So this is what they mean when bubbles up through the water. Bubbling up, bubbling up, bubbling up. Well, as it goes to the top, since this is a gas, as it goes to the top of it kind of starts, looking something like this, as that red gas, and it's not really red, this is like bubbles of gas. So as those bubbles of gas are kind of filling into the top, so I've got an empty top. And I've gotten rid of all the water has kind of been displaced, and so I end up with something looking like this. So now my test tube is no longer full of water, it's now full of whatever this red gas is, which is probably some sort of clear gas, and no more water. So then up here, what I've got is gas from the reaction and water vapor that kind of stuck to the gas as it bubbled up through the water. So I've got gas and water vapor. So that's why this says the total pressure is equal to the pressure of the butane plus the pressure of the water. So my reaction, which I guess in this case is butane, has got butane and water vapor in the top of that test tube. So now, back to the problem. If the pressure in the tube is 765 torr, which means total, that's 765 torr. Then what's the pressure of the butane, and use the water vapor pressure chart. So at 25 degrees, which is what we have, water has a pressure of 24 torr. So water equals 24 torr. Which means butane, which is left over, has to equal 765 minus 24 is 741 torr. Because what I need is the total pressure to be equal to the water plus the butane, or the total pressure minus the water equals the butane. So let's do another one. A 5-liter container holds carbon dioxide and oxygen gas. The carbon dioxide has a pressure of 3 atmospheres. CO2 equals 3 atmospheres. And the oxygen has a pressure of 5 atmospheres. Find the pressure in the container. Essentially what we're looking for is the total pressure. Well, if the carbon dioxide is 3 and the oxygen is 5, all I got to do is add those together. The total is 8 atmospheres. That's it. You're done. That's the end of your problem. But it does get a little trickier than that, I'm sure you know. So let's see. If 1.2 moles of oxygen, so 1.2 moles O2, and 3.6 moles of nitrogen, 3.6 moles N2, are collected in a gas tube, and the total pressure is 800 torr. So 800 torr total. Determine the partial pressure of the oxygen. We're looking for the oxygen only. Okay, so from this information I could tell the total number of moles. If I add these together, I end up with 4.8 moles total. And I know that I have 800 torrs total, so essentially this is a proportion. If the oxygen is 1.2 out of 4.8, what will the oxygen be out of 800? If the oxygen is 1.2 out of 4.8, what will it be out of 800? So that's just a cross-multiply problem. Let's pull up my little calculator here. Multiply the numbers that are across from each other and divide by what's left. That's 1.2 times 800 divided by 4.8 is equal to 200 torr for the oxygen. So what about the partial pressure of the nitrogen? It's the same idea. 3.6 moles out of 4.8 total is equal to how many out of 800 total? So again, across multiply, 3.6 times 800 divided by 4.8 equals 600. So this is going to be 600 torr for the nitrogen. And that actually makes sense because 200 plus 600 equals 800. So they're supposed to add up to get to the total. So essentially what we're just doing is looking at a ratio of pressures, partial pressures to total pressure. All right, last one is Graham's law of effusion. So this has to do with, let's just say you have a balloon, and that balloon is filled with, let's say, helium gas. And that balloon somehow develops a little leak, and just a little leak. So your balloon doesn't like immediately pop, but it just gets smaller and smaller and smaller over time. So you know that that helium is leaking out of your balloon. So let's say you have an identical, pretend these are identical balloons, and this one's filled with, oh, I don't know, neon, some other random gas. And this balloon also has a pinhole leak in it. And so that neon just leaks out over and over and over time. So the question is, which one is going to get smaller faster, or which gas is going to escape quicker? And so Graham's law has to do with the velocity of a gas that effuses through a hole rather than diffuses through a room, but effuses through a small pinhole. So these V's, first of all, these V's are equal to velocity, or speed of a gas. So say the velocity of helium, or the velocity of neon, or how fast a gas is moving. And so it says that the velocity of one compared to the velocity of the other is equal to the square root of the inverse of their molar masses, mm2 over mm1. So let's just say if I was looking at these balloons with helium and neon, we could say the velocity of helium, or how fast the helium moves, compared to the velocity of neon, or how fast the neon moves, is equal to the square root of the molar mass of neon divided by the molar mass of helium. And essentially, when you look into that law, what it's saying is the gas that weighs less moves faster. So I'm going to let you come up with your own example in your own real life of something that is smaller and yet moves quicker. I'm thinking of something like an elephant versus a cheetah. A cheetah weighs less and is able to move much quicker than an elephant can because it weighs so much more. But think of your own kind of example here. So let's see how this works in a math problem. Oh, and here we have helium and oxygen instead of neon. So let's just say we have helium and oxygen under the same conditions of temperature and pressure. Which one has a greater velocity, or which one moves faster? So this you're going to need your periodic table for. You can just look at the one on the wall, or you can just trust me. Helium has a molar mass of approximately 4, and oxygen, since it's O2, has a molar mass of approximately 32 grams per mole. So every 1 mole of helium weighs 4 grams, and every 1 mole of oxygen weighs 32 grams. So in this scenario, oxygen is the elephant, and the helium is the cheetah. Which one moves faster? That is the helium. Helium moves faster because helium weighs less than oxygen, if all other things are the same except for their molar masses. So find the ratio of the velocity of helium to the velocity of oxygen. That's where that formula comes in. The velocity of helium compared to the velocity of oxygen is equal to the square root of the inverse of their molar masses. That's the molar mass of oxygen compared to the molar mass of helium, which, if I say that again, that's 32, because that's the molar mass of oxygen, compared to 4, which square root of 32 over 4. Let's calculate that real fast. The square root of 8, and please don't leave it as the square root of 8. I know your math teacher would have you do that, but please don't. Please let's actually square root the 8. So you end up with 2.83 approximately, which means that helium moves faster. How much faster? 2.83 times faster. Let's try another one. So given nitrogen and argon, again, 2 separate different gases, same conditions of temperature and pressure, and if velocity increases, if something goes faster, then it takes less time. So which has the greater velocity? So we need to look on the periodic table and find out the masses. Nitrogen is 14, but there's 2 of them, so the molar mass of nitrogen is 28, and argon is 39.95. That's going to round up to, let's just say 40 for now, just to give us some good round numbers. So which one has the greater velocity? The greater velocity is the one that moves faster. That means higher speed. So the one that has a higher speed is the one that weighs less, so that'd be the nitrogen. So compare the velocity of nitrogen to that of argon. Compare velocity of nitrogen to the velocity of argon. And so the velocity of square root of the inverse of the molar masses. I need molar mass AR compared to molar mass N2. Molar mass is just the mass of a mole. That's just the mass off the periodic table. And argon we said was 40, and nitrogen we said was 28. So I need 40 divided by 28 is, let's see, square root of 1.05. Square root that right there, 1.03. So what that means is nitrogen moves faster. How much faster? 1.03 times faster. So I'm going to write that here. Nitrogen is 1.03 times faster than argon. So, given nitrogen and argon, same conditions of temperature and pressure, velocity increases, time decreases. Here's where the actual meat of this law comes in. If it takes 5 seconds for a given amount of nitrogen to effuse, how long will it take the same amount of argon? So we know that nitrogen is 1.3 times faster than argon. So if it takes 5 seconds for nitrogen, should argon take more time or less time? If velocity increases, time decreases. So nitrogen is faster, so nitrogen should take less time. So how much less time? 1.03 times less time. We're going to take 5 seconds times 1.03. And I end up with 5.13 seconds. 5.13 seconds for argon. Argon should take more time because argon has a slower speed. So if it takes 90 seconds for argon to effuse, then how long would it take the same amount of nitrogen? So this time we're going to try to make the time get less instead of the time get more. Argon should be the one that's slower. So how much slower? 1.03 times slower. So this time we're going to take the 90 seconds divided by 1.03. I need this to be a smaller time, which gives me 87.4. If you're not sure if you're supposed to be multiplying or if you're supposed to be dividing, if you can remember whether we're supposed to take more time or if we're supposed to take less time, that'll help you look and see if your answer is reasonable. Okay, so that was Avogadro's law and Dalton's law and Graham's law, and I hope that that made sense to you, and if not, please go back and rewatch and pause and rewind and speed up and slow down, and have a great day. I'll see y'all later.